From packet to wakeup. Every video in this series ends the same way. The kernel reports a socket ready. This is what happens before that, from the wire to epoll wait. A frame arrives at the network card. The driver has already posted empty buffers to the card's receive ring. The ring is a circular array of descriptors in main memory, shared by the driver and the card. The card writes the frame into the next free buffer by DMA and marks that descriptor filled. The CPU copies nothing. The card raises a hardware interrupt. The handler does almost nothing. It masks further receive interrupts and schedules NAPI polling. A softirq then drains the ring in batches, commonly 64 frames per poll. Under load, interrupts stay masked and the kernel keeps polling. One interrupt can cover thousands of frames. Each frame is wrapped in an SK buff, the kernel's packet structure. It moves up the stack in place. Ethernet reads its header. IP validates and routes. TCP checks the sequence number and sends an acknowledgement. Each layer advances a pointer past its header. The payload lands on the socket's receive queue, still uncopied. Back when epoll-CTL registered this socket, epoll attached a callback to the socket's wait queue. Once, at registration. Now the payload arrives, and the socket calls SK data ready. That runs the callback. It links the socket onto epoll's ready list and wakes the thread blocked in epoll wait. Readiness is pushed at packet arrival. Nothing is scanned. That is why epoll wait costs O of ready. The full path. The card DMAs the frame into a ring buffer. The interrupt schedules a softirq, and NAPI drains the ring. The stack queues the payload on the socket. The callback puts the socket on the ready list and wakes epoll wait. Your event loop, or your routine, runs. That is how a packet becomes a ready socket.